Hey, Timmy, you look like you could use some help.
Yeah, I've got so much work to do.
Let me explain to you the different solutions for visibility in computer graphics.
Okay, but I'm actually trying to work on this physics homework.
That's great. Here's the textbook
Okay.
for you to follow along. In computer graphics, we are trying to display a three-dimensional scene on a two-dimensional screen. To do this, we have to determine which objects or parts of objects are in front of others, and are therefore obstructing the crap behind them. Here you see Jose Cuervo obstructing the view of Timmy.
Hey, what the hell's going on?
You don't see the objects behind the Jose Cuervo because the Jose Cuervo obstructs the view of them. Can you think of any way of solving this problem?
Well, actually, if you,
That's great! We will discuss 3 different ways of solving this problem, the first of which is the painter's algorithm.
Yay, I like painting!
Painters also have to represent a three-dimensional scene on a two-dimensional canvas. A method that they use to do this is to paint objects in decreasing distance order. This means that the furthest object is painted first and the closest object is painted last, as shown in this picture where 1 is the first object painted and 7 is the last object painted. But in the real world, some objects can have parts in front and behind other objects, such as this example. This is where the painter's algorithm becomes difficult to implement.
This makes my object itchy.
After this long explanation of painter's algorithm, it's actually quite useless in computer graphics, and you can forget all about it.
Okay, but what about my idea to...
Good idea, Timmy. Now let's move on to something computer scientists actually use. Binary space partitioning trees. But since computer scientists are extremely
lazy,
efficient, we call them BSP trees.
Is that like my PSP?
Here's a demonstration of how BSP trees are created. As each object is formed, the tree structure records what is in front and what is behind the current object. Using this data, we create a binary tree. By traversing this binary tree in a in-order mutant traversal method, we can determine the correct order in which to render objects. The left child of each node represents objects that are in front. The right child of each node represents objects that are behind.
I don't believe you! I want my mommy!
You're right, Timmy. There are downsides to using BSP trees. Because building the BSP tree requires a lot of computations, therefore it is only effective for non-moving scenes. Also, the algorithm sometimes splits polygons for tree formation, which can substantially increase the number of polygons in a scene.
Ew! Polygons are nasty!
The final method for solving the problem of visibility we will see today is using a Z-buffer. What the painter's algorithm couldn't accomplish, Z-buffers can. Z-buffers are used to store the distance of each pixel along the Z-axis, similarly to how a frame buffer stores red, green, and blue values. When it's time to display the scene, only the pixel value with the closest Z value is actually rasterized. A downside to using a Z-buffer is that it requires extra memory, and memory costs money.
So how would I perform a 3D transformation and add texture and maybe some cell shading?
That's great, Timmy. I hope you've enjoyed this lesson on visibility in computer graphics.
English, motherfucker, do you speak it?